All right, guys, let's think about an interesting question. We're gonna talk about infinity, and the topic is infinity. And I think that it's kind of profound topic and also seems very difficult. But we're gonna start simple. Let's imagine um, this series. This is the set of all natural numbers. Natural numbers. Basically, the counting numbers. Basically, the things that you could represent using fingers and toes, right? From when the first time you start learning how to count, you learn that okay, if you hold up one finger, that represents one. If you hold up two fingers, it represents two. But you recognize early on that if you do keep on doing this, it just would not end. Like you can think of a very big number. No matter how big the number is, as long as if you add one to it, that number is bigger. So think about a number, let's say gamma, being a very big number. You can always create a new number that's bigger than gamma, namely gamma plus 1. And you can create another number that's bigger than this number, gamma plus 2. Okay? So the question is, what is the size of this this set? Um, so so the natural numbers forms a set. So typically is represented by a capital N. So capital N represents the set of all natural numbers. Set of natural numbers. And it would be something like, okay, 1, 2, 3, 4, 5, etc. Now, how big is this number? It's equivalent to what is the size of this set, right? This sequence of numbers. So maybe whatever the size of this infinity is, so we can ask what is the size of this infinity? Okay, maybe we might not have a definitive answer of what the size of this set is, the set of natural number is, but maybe we can ask some other questions, like maybe um, whatever the size of this is, let's call it aleph null for now. Like what is the size of the natural number? Let's call this like you know aleph null. Well, this is a symbol, and we just say that the size of the natural numbers is aleph null. So typically, when we talk about the size of a set, we represent it by two verticals. Like, so this is the natural numbers. If we have two bars like this, this means the coordinality or the size. The coordinality of the natural numbers. Okay, and maybe we could say that for now, let's say that the size of the natural numbers is aleph null. All right, and by the way, this is actually what the expert call it as well. Maybe we could. So, what's the use of thinking about labeling it as such? Well, it turns out that there are other sets or other other type of number sets that also have the same coordinality as the natural numbers. And we're going to go over some of these examples. Take, for example, let's say we define the set S to be the set of all the set of all even numbers. Let's say you have etc. Again, what is the size of the sequence? By the way, this can be represented by something like this, right? It's 2n, where n is the set of natural numbers, right? Now, there's a way of looking at the set of even natural numbers as being equivalent to the same size as the natural numbers, right? And how do we see this? Consider the following, right? If you can kind of think about it this way, think about 2 as being 2 times 1. 4 is really just 2 times 2. 6 is really 2 times 3. 8 is actually just 2 times 4. 10 is really just 2 times 5. And 12 is just 2 times 6. And you could think about it as this the first element corresponds to 1. The second element corresponds to 2. The third element corresponds to 3. The fourth element corresponds to 4. The fifth element corresponds to 5. Sixth element corresponds to 6. Notice that this is the set of all natural numbers, right? And then this is just S. And from looking at this, if the size of the natural numbers is L null, then that means that the size of the set of all even numbers, right, positive even numbers, has to be also L null. And so this is actually a major result, right? Like, a lot of people would consider the set of even numbers to be, larger or maybe smaller than the natural numbers, but it turns out that they have identical size. They can be represented by L null, the coordinality of their respective set. Now, let's go into a more non-trivial result. Let's think about the set of integers. What is the size of integers? So the integers can be represented by, -5, -4, -3, -2, -1, 0, 1, 2, 3, 3, 4, etc. So, etc., etc. It's basically all integers, negative integers, positive integers, and of course you have 0. What is the size of the integers? By the way, the set of integers can be denoted by a capital Z. So this is a capital Z. What is the size of capital Z? What is the size of integer? Well, it turns out that the size of the integer is also out null. And how do we know this? Well, if there is a way of mapping, we can show this by, you know, seeing if there's a mapping between the elements in the set of integers and the natural numbers, right? Consider, so remember the integers is really just integers, like positive integers and negative integers plus 0. So why don't we rearrange the set of integers in the following way? We're gonna start with 0, then negative 1, then positive 1, negative 2, positive 2, negative 3, positive 3, negative 4, positive 4, negative 5, positive 5, etc. If we organize the set of integers in the following way, we have a starting element, namely 0. We have a negative number, we have a positive number, negative number, positive number, negative number, positive number. And then this doing, you look at this progression, right? It can be conceptually mapped with the natural numbers, right? We can see that the first element, 0, can be mapped with 1. The second element could be mapped with 2. The third element could be mapped with 3. The fourth element could be mapped with 4. The fifth element could be mapped with 5, etc. And that's just the set of all natural numbers. So the set of natural numbers can be mapped with the set of integers in the following way. And because of that, and this is a very non-trivial result, right? Which is the cardinality of the integers is really just L of null. So this is a very, very important result. Okay. Now, what about another interesting non-trivial results would be the set of what is the size of the rational numbers. So what is a rational number? Basically fractions, basically. So the rational numbers, let's not change colors now. Rational numbers are basically numbers where there is a p and then there's a q, where p and q are in elements in Z, where the Z is going to be the set of integers, right? And that Q cannot be equal to 0. Because if Q is equal to 0, then the fraction is undefined. So you can define the set of rational numbers. Oh, by the way, a notation for the rational numbers is Q. So we can define the Q as P implies P divided by Q, such that P and Q are in the set of all integers and Q is not equal to 0. Okay. The question we can ask is what is the size of the rational numbers? And I would show that, and this is a non-trivial result, I think, is that the size of Q is equal to L of null as well. And the way we can show that is to have some sort of mapping between the elements in in Q, or the rational numbers, and the natural numbers. So without loss of generality, we can focus ourselves exclusively with the positive rational numbers. Namely, basically the positive fractions. Okay. In this case, if P and Q is a fraction, we are gonna say that P and Q are positive or bigger than 0, and of course Q is not equal to 0. Okay. We are going to represent this fraction by building up a table. Here in the column, we're going to represent it by P. And so the numerator is represented by P, and the denominator is represented by Q. So suppose that we have 1, 2, 3, 4, 5, 6, 7. So these are the value for the numerator. Q are the value for the denominator. 1, 2, 3, 4, 5, 6. So here, if P, what is the value of here? Like 1, P, what happens when P and Q is identical to 1? Well, it's going to be like this, right? Well, that's just the same thing as 1. What about here? Value for here. Well, it's going to be the numerator, it's going to be 2. Denominator is 1. So it's going to be 2 over 1. And that's just going to be 2. This is going to be 3, 4, 5, 6, 7. How about here? How about the first column? Well, first column is such that the numerator is 1, the denominator is 2, 3, 4, 5, 6. Well, it's going to be 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6. How about here? How about 2 and 2? But that's just 1. How about here? It's going to be 2, 3. Here it's going to be 2, 4. But that's just going to be 1/2. How about here? It's going to be 3, 2. 3, 3. That's just identical to 1. Here is going to be 3, 4. Okay. So there are these entries that do have the same value. And so if there is entries that have the same value, let's say this is 1, right? Then there's another 1. So we just ignore it. So let's find a mapping. So let's say we start from here, right? We start from the first entry, which is on the top left-hand corner. Start with 1. And then we go down like this. second element, third element, fourth element, one, two, three, four, fifth element. So the fifth element is going to be 1 again. So we're going to skip this, all right? We go down the table in this zigzag manner. So we are going to continue to do that, but basically the pattern is that we're going to have, this is our table, we're going to do this. We zigzag across all of the elements. But by zigzagging across all the elements in this table, basically we are mapping the set of all natural numbers with the set of all positive fractions, positive rational numbers. So that means that if this mapping works, which it does, right, then the size of the natural numbers has to be equal to the size of the positive rational numbers, which is, of course, I love no. Now, since we are not just exclusively focusing only on the positive rational numbers, we are also, the rational numbers is, you know, just is the positive rational numbers plus the negative rational numbers plus the element 0, right? So you can think of the positive rational numbers as represented by this triangle, right? Where you can zigzag across the entire table. But you could also represent the negative rational numbers also by a table. But in this case, it's going to be negative, right? You could imagine combining the positive rational numbers and the negative rational numbers in a much larger triangle. Much larger table, right? So you can have the first element could be 1, and then you could have, let's say, just like, we could have, this is probably 2, 3, 4. Maybe you could say, maybe you can have something like -1, and then this is +2, -2, 3, -3, and then similarly you can go down like this, right? -1, 2, -2, etc. And then this is P, and then this is Q. That way, you could also represent like this, right? By doing this, right, we see that the set of the positive rational numbers and the negative rational numbers has the same size as the natural numbers. And all we need to do is maybe one more thing. We could just add the element 0 in there, and we can see that the size of the rational numbers has to be equals to the natural numbers, has to be equals to L of null as well. So far so good. And this is a really interesting result, that the size of the rational numbers is the same as the size of the natural numbers, which is also has the same infinity as the L of null, the size of the natural numbers. But we're gonna go over this very non-trivial result, which is we're gonna assert that, or we're gonna claim that the size of the real numbers is going to be bigger than the size of the natural numbers. So what is the real number? Real numbers are rational numbers, right? We cover that, which is fractions, right? We're talking about integers. How about the irrational numbers? So the real numbers really captures all of the integers, rational numbers, and the irrational numbers. We're gonna claim that the real numbers, actually the size of the real numbers is much more greater than the size of the natural numbers. And how is it gonna go? Okay, so this is a sketch of the proof. Okay, yeah, we start. Suppose that there is a natural mapping between each of the real numbers and each of the natural numbers. And suppose that we are confining ourselves between 0 and 1. So we look at all the real numbers. We between 0 and 1. All right. So it would be numbers such as 0, 1, 2, 3, 7, 8, 4, 2, etc. Or it could be 0.9, 4, 9, 4, 2, 3, blah, blah, blah. Nothing go beyond 1, and nothing go below 0. Right? Suppose that there is a mapping of the real numbers with the natural numbers. Suppose such a mapping exists. So let's say you have a 0, and suppose our first. Let's suppose that this is the natural numbers, right? And suppose that this is the real numbers. Oh, by the way, a set representation of the real numbers is R. So let's say the first number is going to be, let's say A1, A2, A3. And let's have a better notation than this. Suppose that this is going to be 1, 1, 1, 2, 1, 3, 1, 4, blah, blah, blah. So each of these a sub 1, 1, a sub 1, 2, a sub 1, 3, they represent integers. Okay, integers. And these are integers. And okay, So let's suppose the second natural number is mapped with 0, 1, 2, 1, a 2, 2, a 2, 3, etc. Let's suppose that the natural number 3 is mapped to 0, a 3, 1, a 3, 2, a 3, 3, etc. 4 is mapped to 0, a 4, 1, a 4, 2, a 4, 3. Okay, so suppose that for the sake of contradiction, that each of the real numbers can be mapped to each of the natural numbers. So for each of the real numbers on the right correspond to one of the natural numbers on the left. I claim that I could construct a number, let's call it B, that isn't in this list. I'm going to say that B is going to have the value of 0, point B1, B2, B3, B4, B5, etc. Such that B1 is not going to be the same as A sub 1, 1. B2 is not going to be the same as A sub 2, 2. B3 is not going to be A sub 3, 3. B4 is not going to be A sub 4, 4, etc. If you construct, so what I mean is that you could suppose that A sub 1, 1 is 0. Let's say is 0. Then I could pick B1 to be, let's say, 2, right? Suppose A sub 2, 2 is, let's say, 7. I could always pick B2 to be 8. If suppose A sub 3, 3 is 9, I could pick B sub 3 as maybe 4. It's just I have a lot of choice on what I can pick, right? As long as I can pick a number that is not the same as the right hand side, A sub 3, 3, I could pick an 8, right? I can pick a 7, just something that's non-identical to the right hand side, right? I have I have a lot of liberty here. Suppose A sub 4, 4 is gonna be 7. I'm gonna pick, let's say, 3, right? Then I could construct, say, B to be something like, okay, so it's gonna be 0 point, this is gonna be 2, 8, right? 7, 4, 3, etc. And I'm claiming that this number B is not going to be in the list. Is not in the list. But remember, our presupposition is that every real number can be mapped with the natural numbers. But now we have derived a number B such that it can never be in any of the real numbers on the right side of the ledger, on the right side of the list. So it's not going to correspond to any of the natural numbers on the left. So now we have a contradiction, right? A contradiction is that we presupposes that there is a mapping between the natural numbers and the real numbers, and we arrive at a conclusion where there are numbers that are in the right side, that that we have a number that is a real number, but it's not in any of the rows in this list. Ergo, it follows that it, that the size of the real number is much more bigger than the size of the natural numbers. The size of the rational number is greater than the size of the natural numbers, which is no. So, and this is a non-trivial result. And some say that the size of the real numbers is equal to the size of the continuum. The continuum is just basically the size of the numbers, or the size of the set between 0 and 1, all the real numbers between 0 and 1. I think it's also known as the no, the first. I think yeah. I just we can end there. Right. Thank you so much.